On we go with more event perception. And as I finished it last time, we were talking about the idea that emotions, especially in these point light displays, but motions in general, carry information. They carry information about objects and they carry information about events. But I had also said something at the end about whether they indicate causality. And I didn't really deeply explore that question. I just hinted at it a little bit. What am I talking about? Well, when we talked about the ability of the subjects in Johansson's experiment to perceive the difference between a live human being and a marionette puppet, I said that they were very good at that, and it was because of the difference in the way a living animate person moves versus an inanimate puppet, right? And I said there was something about the way in which it accelerates, but that was maybe more information we really need to care about right now. But clearly there is something distinct about biological motion versus non-biological motion, right? And there's whatever that pattern is, some form of acceleration or what have you. What that essentially means is that the motion is carrying information not just about the object itself, a person versus a puppet, but also about the lifefulness or the animacy. I don't think lifefulness is a word, but the animacy of the person and the inanimacy of the puppet. And this relates to cause and effect, because it is the fact that a living person is alive, biological, and animate that they generate that kind of motion. There's a cause and effect relationship between the animacy of the person and the nature of how a person moves. And so by perceiving only the motions, which are the effect, right? Animacy is the cause and motion is the effect. But what we can see with our eyes are simply just the motions. And then the idea is that from that, we are then able to see their cause, which is the animacy of the person. So what I was suggesting there is that motions can specify their cause or provide information about the event in the world that causes those motions to occur. That seems like a not terribly odd thing to say, except it is in fact considered to be a long-standing falsehood from the perspective of philosophy. What? So I'm talking about this guy, David Hume, an old philosopher. And he gave us, among many of the philosophers of this era, a lot of the main influences in perceptual psychology. And what did Hume say about this in particular? He says, now I want you to imagine a situation. I have this example at the bottom related to billiard balls, right? So imagine you are watching someone play billiards, pool, what have you, and you see one ball rolling and it collides with a second ball, and we see that second ball rolling away, and it seems to us completely normal to say something like, that ball, the first ball caused the second ball to move, right? I am assigning a cause and effect interpretation, you could say, to the event that I have watched, right? Hume says that we cannot ever truly justify that statement from a perceptual perspective. And what does he mean by that? He means that when I see this event take place, all that I really have seen is the motion of the first ball followed by the motion of the second ball. Namely, that I've seen a succession of events. One thing moved, and then a second thing moved. And from that alone, That is Hume's description of what is available to the visual system, is merely the fact that I have perceived one thing move and a second thing moved. The temporal succession. This happened and then this happened. But Hume argues that simply because two things happen in a sequence like that doesn't prove that the first thing caused the second thing to happen. Where have you heard that before? Remember stats. I hope you've had stats. But you've heard the phrase correlation doesn't prove causation. That's literally what Hume is saying here, right? He's saying basically that when I perceive the first ball rolling and hit the second object which rolls away, that I haven't seen the causation. What rather I have seen the correlation, right? The senses can only provide us with information about the correlations of different events like that. But any attempt that a human makes to try to assign cause and effect to that observation is merely what Hume calls a mental habit, or maybe just more in common language, we could say that that's just our belief, right? That we come to believe that such events that look like that involve cause and effect, but we can never truly prove and therefore never truly know that we can perceive cause and effect. Essentially, the force, the implicit, physical idea of force equals mass times acceleration, that force that actually causes the acceleration of the massful object here cannot actually be seen. We can only see the mass and the acceleration. So if you think about Newton's second law, F equals ma, right? A force is what causes a mass to accelerate. So we can perceive the mass or the acceleration of objects, but we cannot perceive the force, perhaps, right? Actually, when it comes to vision, I would think it's fair to say we only see the acceleration. But because we can touch on an object, we can hold it, we can experience its mass too in the end. So Hume gives us this weird idea that there's no way for motions to carry information about their cause, right? And that applies not just to our colliding billiard balls, but to all these other things that I've been talking about biological motion. Well, we can fast forward a couple hundred years here. And what we're going to see is Belgian, I think he was Belgian perceptual psychologist, Albert Michat. So what does Michat do? He basically does an experiment to prove that Hume is wrong. That's nice, right? Because there's a lot of things that we might see in some forms of psychology that are essentially philosophy turned into science, and then we get psychology. This is an example of that. So what Michat wants to claim, he has a hypothesis. He says that I think it's true that motions do carry information and significance about their underlying cause. And so he would say here that the motions have an intrinsic significance, meaning an intrinsic meaning. They're informative. And it's related to what we'll call their specificity, as I'm saying here, right? Specific motions. And that means, of course, that if an object moves in one way, that has a certain intrinsic meaning. And then if it moves in a different way, now we have a different, form of, or shape of motion or trajectory of motion, it has a different meaning. But one of the things that Michat did is that he not only does an experiment where he presents people with objects moving in characteristic ways, but he also eliminated the underlying causal factors here. That could be possibly a confounding variable that you can never really truly say that someone is perceiving the event or the cause of the event. They're going to use both words at a perceptual level. But if we eliminate the cause and make it make this something of a fiction, what am I talking about? Well, let's have a look at the event here. This doesn't look like anything, right? What we have on the left of this frame, so we built this frame, right? And this frame has this big white disc that can spin around. And painted on the disc, you see the red curve and the black curve, right? And on the bottom, those of the disc, you see that the curves are separated a little bit. But as we move up to the left side, they come into contact with each other and they stay touching each other for a while, and then they start to move apart again, right? Now, if you notice on the right-hand side of this frame, there's another kind of panel there. And it's hard to see, but right where my mouse is pointing, there is a small little window in this. This is an opaque cover, right? There's a small window in it. And this is actually on a hinge. It's like a door. So what we're going to do is we're going to close the flap here, the cover. And when that happens, we're only going to be able to see these red and black curves here, not as the whole curve, but we're just going to be able to see it through a little window, like a narrow slice of it, right? I have an attempt at trying to depict that over here, right? So here we see the panel is closed, and this dashed rectangle here is showing what the subject can see, is whatever's inside this little window here, all right? So what happens is we spin the disc after we close that door, and the subject can only see it through the little viewing window. And when we spin the disc, what's going to happen, let's come back to here, is that we're going to see a little red rectangle or red box and a black box inside of that window. And if you look at my hands, what that's going to happen is that the two lines start far apart, so the black and red dots are going to appear far apart. And as we spin the disc, they get closer together, they come into contact with each other, and then they move apart again, right? And that's drawing those lines however you want. You're going to be able to draw all kinds of different, essentially simulations of collision events, right? Two things come together and then bounce off. But what Machat did was he manipulated how much time the two objects appear to be linked with each other. Because in a typical collision event, and again, you try to watch my hands here, in a typical collision event, it's going to be really immediate, right? You don't think you're just going to have this immediate kind of launch effect that occurs. But if we did something else where I stuck the two objects together for just an extra second or so, the overall pattern of the event is the same, right? You have one thing happening and then another thing happening. And so you would imagine, if you are Hume, that you would make no particular distinction between these two events, right? Hume is saying that, the specific form of the event doesn't matter, carries no inherent meaning, and therefore the timing doesn't really matter, whether they pop together very quickly or whether they stick together for an extra fraction of a second, shouldn't matter. There is no meaning carried by the motion. All that you're seeing is just two successive events, one thing followed by another thing. If that was true, and if Hume was correct, then we might expect that people would label both events with the same word, which would be causation or launching, right? Essentially the same event when it comes to just the succession of one thing followed by another thing. So Hume would predict that people ought to treat these two events as being both cause and effect, the same kind of regular causal launching. So that's what I'm trying to describe here with Machat, right? He's basically creating a simulated event so he can describe any kind of motion, simulated motion that he wants to, various arbitrary combinations of these. This is what it kind of looks like, right? So here a black dot, a black box, and a white box collide with each other. And when there's no delay, no sticking together for a little bit, people say that that's a collision event, a launching event. Now, when we add in that brief delay, so the two objects stick together for a period of time, people call it something else. They just spontaneously come up with a completely new word that they call triggering in some cases, right? The idea is that this really disproves Hume. It basically says that once we make a minor little change in the timing of this event, even though at that level of description, broad level of description, it's simply just a succession of two motions, what's also important is the very specific timing between the two motions. And that specific timing has inherent perceptual significance because changing the timing results in people changing the words that they use to describe it, and therefore it changes their perception of it, right? That's the idea. And so this idea that motions can, in fact, carry information about the underlying causal force in a collision event has now led another guy here, Sverker Runeson, to talk about this some more, right? This idea of motions carrying information about the dynamic forces of the collision. Runeson was, in fact, a student of Gunnar Johansson at Uppsala in Sweden. So carrying on in that tradition of point light displays and this kind of stuff. So, but the first thing Runeson does is he wants to talk about, well, when two objects collide, let's talk about that mass, for example. Again, you can't really see the mass. You just see the acceleration. And so if I watch two objects collide, again, two balls that are rolling together, and then they hit each other, and then they ricochet and bounce off in various directions. Is it possible that I might be able to perceive, if not the exact mass of the two objects, but maybe I can perceive their relative mass? That is, maybe I can perceive that one object is twice as heavy as the other, or massful, maybe is a better word, or 1.5 times as massful as the other. Is that possible for a person to be able to make that kind of judgment? Well, how would we know? How can we prove this, right? Well, obviously we can do an experiment, but before we do an experiment, we need to talk about the idea that there needs to be information. Can we even demonstrate the possibility of there really being information other than just supposing that there could be information? I want to do some math again. And so just as we had done with the tau variable, I want to demonstrate that it is possible to show that not only can we hypothesize the presence of information, we can mathematically determine the presence of information. So here we're going to do some algebra, right? First off, we have this equation that describes what is otherwise known as the law of conservation of momentum. So you may have heard of this before. The law of conservation of momentum says that if you have two objects that are, as shown on the bottom, maybe two balls that are rolling towards each other, we're going to, each of those objects has a momentum, right? Momentum is defined as mass times velocity. Now they're going to collide, and then they're going to bounce off of each other and ricochet off in various directions. And what we're going to find, according to the law of conservation of momentum, is that the total momentum of this system is conserved before and after the collision. That means that even though individual momentums of each individual object might change, their sums must stay the same. So if we were to add up the momentum of object 1 plus the momentum of object 2 before the collision, that should equal the sum of the momentum of object 1 and the momentum of object 2 after the collision. And that's what this first equation is showing us, because we see the m1v1 refers to the mass of object 1 times the velocity of object 1, which is its momentum. And we're going to use the superscript b to indicate before the collision. And likewise, we're going to get the momentum of object 2 before the collision. And so we have that sum. And on the right-hand side, we have the momentum of object 1 after the collision and the momentum of object 2 after the collision. Those two sums equate. Now what we're going to do is we are going to do some more algebra here. We're going to rearrange this equation to factor out the mass from the velocities, right? So what I want to do is I want to get the mass of object 1 on the left-hand side and the mass of object 2 on the right-hand side. And so I could just subtract that out, right? That's this basic algebra. So if I subtract M2, V2 before the collision from both sides, then we lose it from the left-hand side and we add it to the right-hand side. And then likewise, if I subtract the momentum of object 1 after the collision from the right-hand side and the left-hand side, then we get that on the left-hand side too, right? And then once we do that, we can then factor out the mass, because the mass is the same, even though the velocities might change. The mass is going to stay the constant, right? We're not colliding these objects at such high velocity that they start to break apart, and lose little bits and pieces. So the mass is going to be constant, and that's what we end up with here is this difference velocity of object 1 before the collision minus the velocity of object 1 after the collision within parentheses times its mass. And that's also then equal to the velocity of object 2 after minus velocity of object 2 before, all times its mass. And then what we can further do is we can do a little bit more algebraic rearrangement and divide both sides by the mass of object 2, as well as divide that out by the object 1 velocities. And so what we're going to end up with is this little set of ratios on the bottom. M1 over M2 is equal to this weird velocity ratio of object 2 after minus before, and object 1 before minus after. So what's the whole point of all of that? Well, the idea is that, as I said before, when we perceive an event visually, maybe we can't see the force directly or the mass directly, but we can see the velocities and the accelerations, right? We can see the motion. And so if I am able to see the motion of the objects before they collide, and then look at the motions of the objects after they collide, those ratios of the velocities before and after, in principle, equals the mass ratio. So what this now is suggesting is that seeing the velocity change before and after the collision is equal to perceiving the mass ratio of the objects by natural law, because this is a law of physics, right? And so by natural law, a law of physics, the visual pattern of the velocity change before and after the collision directly equals the mass ratio, and therefore provides information about the mass ratio. So do people correctly do this? Do people correctly use this information? Well, what Runeson found in 1977 was yes. That's exactly what happens, is that if we manipulate these, create simulated collisions and manipulate the before and after velocities just so, people are going to judge the mass ratios of the objects just as you would mathematically predict them to do. And then a couple of years later, Rudison and colleague here, Gunilla Frickholm, do some other studies where they are continuing with this idea of perceiving mass, or in this case, weight, which is mass times gravity. But they're doing it with these patch-like kind of displays. So here we see our actor wearing reflective patches on a black bodysuit. We film them in the dark with the light shining on them. So we see the points of their joints as they lift various boxes. Runeson and Frickholm had both male and female actors in this task. Obviously, they might vary a little bit in strength. And what we're going to do is we're going to ask our subjects to watch the videos and try to judge how much weight is in the box. So sometimes the actor is lifting a weight that's light versus heavy. As you can see on the graph here, it ranged from 4 to 28 kilograms. And then we ask our subjects to just try to perceptually judge how much weight is in the box. And what you find here is very, very excellent performance, right? So the main diagonal line in this graph represents a line of perfect accuracy, right? So in that case, if the actual weight in the box was 10 kilograms, we would predict that the judgment ought to be exactly 10 kilograms, right? And when it's 16 kilograms on the x-axis, you would expect it to be a judgment of 16 kilograms on the y-axis. Well, these lines are statistically very close, almost to the point of being indistinguishable from that line of perfect accuracy. And so this again tells us that people are quite accurate in this task of judging the weight. And therefore, again, the idea is that, the main constraint here is that you have a person who has some degree of limited strength lifting a box. And so something in the way in which the dynamics of that lifting action occurs provides information about the kinematic pattern that results, which is the pattern of velocity and acceleration of the lifting action. So this leads Runis and Frickel, here are their conclusions, right? That again, we can perceive the weight in the box simply just based on the motion by itself. And so, as I had mentioned, this word kinematics. Kinematics refers to the way in which we can measure positions and velocities. So anything that's described in terms of position or length or change of position or change of length over time, which can then have a velocity and acceleration and further derivatives. That's what kinematics is all about. Now, on the other hand, dynamics involves the forces, the actual underlying constraints and things that cause the motion to occur. Gravity, of course, is part of that because gravity is the force of, accelerating force of gravity, right? But cause and effect is another kind of force, right? When one object collides with another, it imparts that force. So Runison and Frickholm's conclusion is this phrase here: the kinematics provide information about the dynamics, and or as the title of this slide says, this is what Runison calls it, the KSD principle. Kinematics specify dynamics. What that also then means is that since the kinematics are what the visual system has access to directly, that means the visual system has access to the underlying dynamics. Again, refuting Hume's idea. Because in this case, if I am perceiving the event kinematics and I get right along with that direct information about event dynamics, then yes, I am lawfully perceiving the underlying causes of the event. Now we can jump to Jim Cutting. And so around the same time, but in the United States, Cutting is doing this research with the point light walkers. And one of the things that became a popular question about Johansson's work was this idea of whether or not people could judge the sex of the actor, right? And we saw that there was 70 to 80% accuracy. But the problem is that Johansson didn't do a huge, well-controlled study here with lots of different actors, and he also didn't necessarily control for the height of the actor in the display, right? You could see that sometimes if you have a man that's taller than the woman in the display, then obviously you could try to judge who's the man and who's the woman simply by who appears to be the taller point light walker. So Cutting addressed this issue by having a large number of actors, both male and female, and he would ensure that they all have the same height in the display by moving the camera back and forth. Right. So if you have a shorter person, you're going to film them at a shorter distance so that you achieve a certain height on the screen in the videos, right? And then if you have a taller person, you move the camera back so that you equate the height of that person on the screen. And so what we're really controlling here is what we call their visual angle, right? How large of a visual angle does each person as a stimulus project? And we're going to equate those things so that there are no real size differences between our point light walkers anymore. And we're going to ask them to walk back and forth. And then the question becomes, can people recognize male and females once we control for these variables? And the answer turned out to be yes, we're still able to do this with very good accuracy. Cutting extended this as well because something else was that he tested was recognizing a familiar person. And so what he did is he had at the university, he went to a dorm and he got a bunch of students from the same floor of the dorm who had all been living on that one floor of the dorm for the whole school year together. So they had become, decently well acquainted with each other. And so he creates point light videos of each one of the students from that dorm, and then creates a randomized display, of all of these different people and sequences, random sequences, and then he shows these things back to these same students, asking them if they can tell who's who. And it turns out they could. So if that's the case, then that again, just a surprising potentially amount of information available via the motion, right? Male versus female, different identities of different people. Now I have the link here. I'll let you, if you download the PowerPoints, you can put that link into your web browser, and you can explore Nico Choi's biomotion lab, in which he has some demonstrations, including some like Flash-based interactive tools to evaluate how much information you can possibly get from a point light walker. But what I want to do next is I want to move it to Bingham's research now, moving into the 80s and 90s. So Bingham is interested in something else that Johansson was doing besides the stuff about KSD, right, that we got through Runeson and Cutting. But the fact that we can look at people performing various actions and recognize those actions, or we can look at the rolling wheel and recognize the rolling wheel, right? So Bingham and colleagues here want to study what we could call then event identification. That is, when we watch an event, how is it that we recognize one kind of an event from a different kind of an event? This is also relevant, by the way, to the Machat research, right? Where that little subtle little change in the event timing by inserting a little delay changes the name that people give to it. And therefore it changes people's perception of what this event is and what's really happening. And Bingham wants to understand this. And so in a way that's very much inspired by the marionette puppet example that Johansson had done, Bingham uses what we're going to call here natural events and hand-moved events. So I have some examples here of a spring, a pendulum, and a rolling ball. Balls like rolling down a ramp, right? So imagine a spring. If I were to have a weight at the end of a spring and I pull it down and let go, what's that spring going to do? It's just going to bounce up and down, right? But it's going to bounce up and down until it dissipates, and then it settles back down and comes to a stop, right? That would be an event. And we could create a patch light version of that by putting some reflective tape on the ball hanging on the spring, and then film that in the dark. And we can, a person will see the patches of light moving up and down again, and then it would settle down to a stop. But what if we had an actor try to imitate this by moving that object by hand? So now what we're going to do is we're going to have an actor who's wearing black gloves hold this patch light marked ball and move it up and down as if it was at the end of a spring. And they're going to try to do it so that they time everything in the exact same way, right? They're going to try to imitate the timing as best as they can and the spatial trajectory. We're also going to do that with a pendulum, right? So again, you think about how an object swings at the end of a pendulum, right? Back and forth, back and forth. And then I'm going to have my actor try to imitate that with the hand moved version. They're going to hold it again with black gloves so you can't see their hand in the display. And you're going to see that object swinging back and forth, following the exact same spatial trajectory and on pretty close to the same timing, right? We'll just count out a metronome that, you got to move at this speed, tick tock, right? And we'll have our actor imitate the pendulum. And the same for a ball rolling down a slope, right? They're going to try to move it down the ramp at the same kind of rate at which you would expect it to fall, or free fall, perhaps, right? So we're going to create these point light displays where we're going to show people these little clips of each event. And sometimes it might be the natural version of the event. Sometimes it might be a hand-moved version of the event. We're going to ask if people can correctly identify which one is which. And they do, right? So again, the idea is that there is just something that is just naturally easy for human subjects to do, which is to recognize two different kinds of events, especially when one involves an animate, human-driven motion, biological motion, and the other one is inanimate. I should say inanimate, but at least not biological motion. So again, there seems to be some kind of an important distinction here, just like Johansson had demonstrated between biological and non-biological motion. But what Bingham wants to do is explore in more detail what is that exact pattern of motion, the velocities and the acceleration of biological motion. I had said before, may be somehow unique and special. So Bingham makes the claim of using this term we've used before of a spatiotemporal pattern, right? But here he refers to the idea of as a spatiotemporal trajectory form. What is that? Well, that is what this is. By the way, you'll find another video in the module, which is me once again using the virtual whiteboard thing in Zoom to try to illustrate these phase portraits a little bit better than just these already drawn ones here. A phase portrait, what's that? Well, a phase portrait is a graph with position on the x-axis and velocity on the y-axis. And that's what we have labeled here, x and x dot. X dot, the dot is sometimes used to indicate taking the first derivative, and the first derivative of position is velocity, right? So that's what we have here. X, a change in position is x, right? The x position, and x dot is going to be the velocity. So we have this graph on the left labeled pendulums, and we're two circles on this graph, right? So what's happening here? Imagine this here. When you have a pendulum that swings, it starts actually. So look at me in the camera window here. It starts up here, and then it swings down, and it accelerates as it swings down, right? And then as it reaches the opposite end of its swing, it starts to slow down again, and it comes to a momentary stop before going back the other direction, right? So you would imagine that you could graph that velocity and position, and the position is going to change on the x-axis here from the far left-hand side of that larger circle to the far right-hand side of that circle. And that's the change in the object's position between one end of its swing and the other. But we also are now graphing the velocity on the y-axis here. So the velocity is actually, as it swings down, is increasing. And then once the object hits the bottom of the swing, it hits peak velocity, and then it starts to slow down as we approach the opposite end. And that's what the top half of this circle is actually showing us, right? It's showing us the initial increase in the velocity of the object, hits peak velocity halfway across, and then as it approaches the opposite end of its swing, it approaches zero velocity. And for a momentary fraction of a second, the object really does stop as it reverses direction and swings back to where it started. And that's actually now the bottom half of the circle. Why are we going in the opposite direction with the velocity? What, negative velocity? What does that mean? Well, that by convention, we're just going to say that velocity in one direction is positive and velocity in the other direction is negative. And in which case now we can circle back to where we started, literally. Of course, we're assuming here an ideal pendulum that doesn't lose any energy from friction and air resistance and that sort of thing. So it will return where it starts. And there we have it. We've completed a whole circle here, showing, of course, how a pendulum is an oscillator. So that particular circular shape is the characteristic phase portrait of a pendulum. But we can also, using Bingham's terminology here on the previous slide, it is the spatiotemporal form of the pendulum. Why are we calling it a spatiotemporal form? Because the x-axis is the spatial axis and the y-axis is the temporal axis because of velocity component represents change in position over time, right? It's the time derivative of x. So there you have it, right? We have a spatiotemporal trajectory form, and the pendulum form is that. Over on the top right, we have the trajectory forms for objects rolling down a slope, or on the bottom, just free fall. Just drop it and let it fall. All right. Now, why do we have different ones? Why are there two circles, a small one and a large one? Why do we have three different little curves for rolling down a slope, or two curves for free fall? Well, it also depends on spatial scale as well. So here, the small circle for the pendulum and the large circle might be pendulums of different lengths, right? So when you have a pendulum that has a short length to it, it doesn't travel so far, right? And therefore that changes its timing, and it changes the spatial scale of its trajectory form. The same goes for objects in free fall or rolling down a slope. Before they hit terminal velocity, there might be a subtle difference in their acceleration, right? Initial acceleration. And you're going to see that there. So this is Bingham's conclusion, that when it comes to the ability of our subjects in those experiments to recognize the difference between the hand-moved version of the pendulum and the natural version of the pendulum, the explanation for that arises from the fact that when a human does it, if we were to graph the actual velocity and position of that event as moved by a human actor, we're going to see that we will not get anything like a perfect circle there, right? We're going to get a highly imperfect circle trajectory form. It's going to be lopsided, right? Because the person is not going to accelerate in such a symmetric way as they go down to the bottom. And maybe they don't hit peak velocity perfectly halfway across, and then they don't decelerate it exactly the way gravity would. So this means that the difference between the hand-moved version of the event and the natural version of the event differ in terms of the shape as traced out in phase space. And some of the other papers that Bingham and crew had done did some computer simulations of these events where that's exactly what they systematically controlled, was minute variations in the shape of the trajectory form as defined in phase space, results in people, he repeats the Mashot methodology, right? And basically saying, give a name to this event. And when you change, in subtle ways, the shape of the trajectory form, people spontaneously give different names and different identities to these events. So again, suggesting that the event identity is directly influenced by the variable that's manipulated here, which is the shape of the trajectory form as defined in phase space. So again, this is a perturbation experiment, going back to that, right? We perturb the shape of the trajectory form in phase space, and this results in systematic changes in people's perceptual identification of the event. The same was also true of the scale as well, right? The idea is that I said we've got the different circles for the different lengths of the pendulums. So can we show the video and ask people to judge the length of the pendulum? So just like with the patchlight walkers, what we're going to do is we're going to film the short pendulum close up and the long pendulum further back. So that way on screen, they both have the same apparent length, but they're going to swing at different rates, and ask people to see if they can judge the size of the object that's swinging or the distance to the object, right? Something about the spatial scale of the event. Turns out, yes, in fact, they can do that too. So just from watching these point light videos of objects in free fall, swinging as pendulums, rolling down a slope, we're going to get these kinds of events that specify event identity, easily recognized as a different kind of an event with a small perturbation to the trajectory form. And also people are capable of recognizing the spatial scale, the size and distance of the event as well. So a lot of information apparently now from the point light research. And now we move into something even more recent, which is the research of Cristina Becchio and many of her colleagues in Italy. What we have here is extending the idea of kinematic specification of dynamics a little bit further into what we might call the kinematic specification of intention. And that's a wild one. And this also really gets at the heart of a lot of core issues in both philosophy of mind and perceptual psychology. Social perception usually says that when I watch another person engage in some action, I have to engage in some form of what we call attribution theory, where I infer why I think that person is doing what they're doing. Do I think that they are being nice and cooperative? Do I think that they are being selfish or competitive? Can I perceive that through a way a person moves? Traditionally, we say no. Rather, I pick up cues about that person's action and facial expression and whatever else they might be doing. And then I use those cues as a basis for my social inference, right? But of course, this is exactly the kind of sensation-mediated theory we've been talking about in perception all along, right? Is that all of the sensations that arrive are simply just cues that are used to drive our perceptual inference. And hopefully we are right, but we are sometimes wrong. And the same is true for social perception as generally understood, that I can't, perceive what other people are thinking, why they do what they do, what their intentions are, but I can perceive certain social cues and then use those cues as the basis for my inference. And hopefully I'm right most of the time, but sometimes I'm wrong. And this, of course, sounds completely natural because it raises the possibility that, sometimes people are good at reading others and sometimes we're not, right? But the possibility of the kinematic specification of intentions does in fact raise the possibility that maybe we can directly perceive the underlying cause of the event, which in the case of human motion, the underlying cause can involve the actor's intentions, right? So if I'm engaging in a cooperative action with another person, then my cooperative intentions are a dynamic constraint on how I perform my actions. And so anyone who sees my actions should be able to see my intention of cooperation. Or if I'm being competitive, that puts a different constraint on how I move, a different causal constraint on how I move. And somebody who witnesses my actions would directly perceive my competitiveness, right? This raises this possibility of direct social perception as being potentially a legitimate hypothesis, which does suggest that, yes, we could actually see other people's mental states, intentionality, and motivation in some more direct perceptual way. It's not just pure inference. This is consistent with other new ideas in psychology, such as the embodied cognition thesis, because the embodied cognition thesis says that our cognitions, including our intentions and motivations for why we do something, are not just abstract states in the mind, but are actually literally embodied. They are part of our action and our embodiment and how we move. And it also, maybe we could speculate the role of mirror neurons in all of this as well. If you've heard of mirror neurons before, this is the idea that certain neurons in the brain seem to have a specialized function, that they are active when we engage in a specific kind of action, but they are also active when we observe another person doing the same action, as if maybe the neurons somehow mirror this, right? I see you do something, and that activates a subset of neurons. And that when I perform that action, I just have to reactivate those exact same neurons so that I can do exactly what you did, right? That's why they're called mirror neurons. So it might be the case that it could explain how I'm able to perceive another person's cooperation, because when they are engaging in an action that is truly cooperative and that cooperation is embodied in their action, it activates my mirror neurons for what I would do if I was engaging in a cooperative action, and there enables me to just immediately and easily recognize the intentions of our other person here. So in Becchio's research, that's exactly what they did. They have actors performing various tasks created point light displays of actors performing a cooperative task or a competitive task, and then they play these videos back to naive research participants, and lo and behold, people can recognize the two events correctly. And I have here some demonstrations of this. Now, these are events that we created here at UCF in our mocap studio. And so, again, these are actors doing something. These are actors that are just picking up, they're seated opposite each other at a table. Can't see the table at all, but you can kind of get a sense that you see two seated people, right? Just from the still frame. And then what they're going to do is they're going to pick up an object and move it to the center of the table. And we just want to know, are they being cooperative as if maybe they're working together to build a little tower? Or are they being competitive as if maybe they're trying to be the first to put the block in the center? So what about these? All right. I'm just going to play this over and over again for a while. And if this doesn't look very good through Zoom, again, I want to recommend that maybe you download PowerPoints to get this to work. But what you can see is that we might be able to make a judgment about this event. And if I come down here, this event might be a little different, right? So which one is which? Well, the top one is competitive, the bottom one is cooperative. Now, you might think, well, there's maybe an obvious thing here, right? The top one was faster, the bottom one was slower. So if that was the case, then what we could do is another experiment where I just have people go fast and go slow, and people would make the same distinctions. Well, they might, but if I played a version of this task where I instructed the subjects to be competitive, and then I also played another version of this task where I just instructed the participants to go fast, or my actors, I mean, do you think that they would treat those two videos as the same? That is, the ones where the actors were instructed to be competitive would essentially be identical to the ones where the actors were instructed to go fast. And it turns out they're not, right? And when I show those two videos to subjects, they can discriminate between the ones where they're actually being competitive versus the ones where they're just going quickly. And the same goes for the cooperative versus slow. If I tell people to go slow or go cooperative, and then I play those videos side by side, our subjects can again easily recognize, I don't want to say easily, but they can at least better than chance recognize which ones were truly cooperative and which ones were where the actors were just instructed to go a little slower. So there is apparently something that is inherently, again, built into the motions here about the event intentionality as well, right? Why is the actor, what is their motivation, what is their intention or plan or purpose for engaging in this action? And this may be now evidence that those intentionalities are truly embodied and acted out in the course of the movement, and can then be directly perceived and recognized by others, right? So that's our final point here, other than a wrap up of the concept of event perception, where these spatiotemporal forms are very important, right? They are very perceptually important and needs to be a central part of visual perception theories to account for perception of change and motion, and not treat the eye as a camera that takes static images or static snapshots of the world. Perception is something that actually is extended over time, right? We are not simply just locked into this razor's edge of the present as perception is just of the current moment, but perception is temporally extended. We are at any point slightly aware of the most recent past as well as the upcoming future moments as well. And so perception is an temporally extended action. And then what happens is that what we get from these spatiotemporal patterns of motion and change is what we're going to call invariance over transformation. And this is actually connected to what I said at the very beginning of the event perception notes, which is that we see something that is changing, which would be all those transformations like rotations and translation and so forth. But then there's also something that stays the same. And that's the invariance. Something that is invariant means it does not change. So embedded within all of these kinds of displays, the point light displays, the kinetic depth effect, all of that stuff, there's a transformation that's occurring, but there's also an invariant pattern that is occurring. And the transformation specifies the change, the invariant pattern specifies the object, and that we always have these two things intimately linked with each other, right? They are inseparable. You can't get the invariant pattern without the transforming pattern. And likewise, every time that transforming pattern occurs, it is also accompanied by some invariant pattern. And so we always get the object and the change together, right? They have to be perceived together, right? That's the theme of the event perception research. And as noted, it's consistent with the ecological approach because it suggests that there's information available to the visual system when that information is defined as a pattern of motion external to the observer here, right? And so what we could go back to the optic flow findings from the ecological psych notes and point out that all of those optic flow patterns, the focus of expansion and the flow gradient and the outflow, inflow, those are all invariant patterns, right? There is transformation occurring because of the optic flow itself, but the ever-present location of the focus of expansion is always invariant with regard to your heading direction, right? And so we get transformations and we also get invariant patterns. And the claim here ultimately from the ecological approach is that what we really are doing is we are detecting these so-called perceptual invariants. That is the invariant patterns embedded within the transforming optic array, right? And that is really the true basis of perception and pattern recognition, and how we perceive objects is by perceiving objects and events together. And well, there we go. We've wrapped up event perception.